Record. Okay, so the first thing we're gonna do is just quickly go over the Crowdmark assignment submission aspect of the course and how you would locate that and how that would work in general. And then we'll go back and complete lecture set 1, which is the lecture set that we started on Thursday. And then we'll move into lecture set 2, which would be the lecture set of focus for this week. All right, so if you go to Blackboard, so this is just probably similar to what you guys see when you log into Blackboard here. So you have a course list down the side underneath the semester term. Our course is this merged course, so ASO1, ASO3 merged. If we click this and we go to course content, there will be an assignments folder right here. If we click this, you can see that there are already a few different links that are in this folder. So the first link is a link that will send you to a YouTube video that I recorded last year. And this YouTube video gives you some examples of how you can submit your answers on Crowdmark. In this video, there are two parts, part A and part B. That's meant to basically mimic the design of the actual assignments. So on our real assignments, we will also have a part A and a part B, where part A corresponds to the lectures and part B corresponds to the lab material. At this point, I don't think all of you would have had a lab yet. So labs officially started yesterday. So some of you might have had a lab and you might have seen R and you might have seen R Commander. But if you haven't yet, then there is the possibility that when you see part B, it's not going to make a lot of sense. And that's perfectly fine at this point. The video demonstration for part B is just to give you an idea of a way that you could get your answers from R Commander into Crowdmark. But I imagine that your lab instructor is going to go over that with you as well. So if you get to this part and you're a bit confused and it doesn't make a lot of sense, don't worry about it. Again, it's just an example of one way that you can do it, which basically is just taking a screenshot of the relevant information. Okay, you'll notice that there are 3 assignments here. Assignment 0. Assignment 0 is a practice assignment. It's not for any marks. It's purely there just to give you practice with using Crowdmark. So if you click the link here with the Crowdmark symbol, so that's what this symbol is here, and it says Crowdmark link on it. You click this, it'll take you to the submission page. And the submission page is going to look something like this. So you'll see that at the top, there's a short description of the assignment. And then below there are a box, or there is a box corresponding to each of or one of the questions on the assignment. So for example, here it says A1. So this is part A, question 1. And then right here, it says drag and drop an image or PDF file or click to browse. So basically, when you're working through your assignments, the traditional option would be that you do it on pen and paper. So you write your answers down and then you take a photo of your answers, your written answers, and then you would simply just upload that photo into the box that's shown here. Now, in assignment 0, I basically give 3 different illustrations of how you could upload your image. So one of the options would again be pen and paper. So you just write it down like you would in the most traditional way. And then you take a picture of whatever you wrote down and you upload the picture. If you're using a tablet, like an iPad or the Windows Surface machine, you could write your answer on your tablet and then you could export the page to PDF and upload the PDF. That would work as well. Or if you were typing out all of your answers, so maybe you use Microsoft Word, for example, or some other kind of word processor, you could also export that to a PDF and then upload that. So there are different options. You don't have to use the exact same option for every single question. You can pick whatever works best for you depending on the kind of question that you're answering. But again, the purpose of this assignment 0, I should say, is to just show you some of the ways that you can get a solution into Crowdmark. And I came up with 3 different ways of doing it, but there's probably others that I hadn't even thought about at this point. As long as you can get a legible, a readable and legible image into the Dropbox, or into these boxes here, that's what I mean by Dropbox, that's more than sufficient. Part B is the same idea, except it's a lab question. So this will typically involve a screenshot being taken of some kind. Another way that you could do this is you can open up a word processor like Microsoft Word. You can type out your solutions, and whenever you need an image, like for example, a graph, you can take a screenshot of that graph and then just upload that into the Word document. And then you can export that to a PDF and just drop the whole thing into the box. Okay. Now, one of the questions that'll typically come up is something like, so say on like one piece of paper, you have 5 different answers. So you have question 1 through 5 written on the same piece of paper. You take one photo. The photo is perfectly legible, but it's a photo of all 5 questions. You can drop the same photo into the box that it needs to be dropped into. So it's perfectly fine. For example, if this box, and this box all contain the exact same picture. As long as it's easy to find the question so the TA can grade it, or so that I can grade it, that's all that matters. It doesn't have to be a unique photo where you perfectly snip just the part of that particular question out and put it into the box. If you want to do that, that's great, but you don't have to do that. As long as we can read the image and find what we're looking for easily, that's all that matters. Okay. Does anyone have any questions about the Crowdmark submission? For the lab part, the data is right here. So there's 2 data sets for assignment number 1. There's statistics student survey for r.xlsx. So this link here, and then there's A1_admission, which is this link right here. So for each of the assignments, there will be a Word doc with the questions, and then the other files will be the data sets for that assignment. All right. Any other questions? That's a good question. I don't know the answer to that, to be honest with you. So we have the first 2 assignments already. Those are the assignments that have been made available. As soon as the next one is available, I'll just continue to open them up for you to review. But I can't say for sure at this point how long in advance. Hopefully about a month, because that seems to be where we're at right now. The due dates are in the course outline. All of the due dates for the lab assignments and the lab quizzes, they're in the course outline. But I think assignment 1 is October. No, that's wrong. September 29th or something like this. 28th. Thank you. September 28th. You got to get to the assignments eventually, so there's no point in putting them off. There's 6 of them. The sooner we start, the better. All right. Any other questions about the assignments or Crowdmark or anything related? I could help with part B at a separate time, like for example, during an office hour or something like this, but that's the lab material. So if you attend your lab section, the instructor for your lab will go over that with you. But it wouldn't be appropriate to do it right now because it's going to take away from the lecture aspect of the course, which is what I need to cover. Alrighty. Okay, so I'm going to stop this. And then I'm going to share this. Okay. Yeah, 67. Not bad, not bad. By the way, 67 is the number of people that are here, not just a random number that I thought of for no reason. Okay, the only other thing I want to do is that. Perfect. Okay, so we're gonna continue with lecture set number 1. I'll just make a note that we are starting here today. So this is September 14th. All right, so last class, we spent a ridiculous amount of time going over the course outline. I think I've been teaching at McEwen for, this is my 6th year. No, yeah, 6th year, 5th year. I don't know. I've been teaching here for a while and I've never spent that much time on a course outline before. So we've set a new record. But after we finished that, we got into the first lecture set, which is the actual material for the class. So it's good that we at least got to it a little bit. We talked about a few different things, mainly just definitions. So the definitions from the first lecture set, the main ones that we focused on were what is statistics? So again, a pretty important definition considering that we're taking an intro stats course. We talked about 2 different types of statistics, inferential statistics and descriptive statistics. We talked about sample and population. So the idea that we in general want to make a statement about a population, but we will usually do this using a sample, which is effectively just a subset of the population. And I drew my little rectangle circle graph here to try and illustrate what a sample would look like relative to a population. And the big point is just like the sample is a subset of the population. So it's a collection of units that we are taking out of the population that we are studying. We also talked about the difference. We finished off, I should say, by talking about the differences between the observational study and the designed experiment. And the key here is that the observational study is one in which we do not apply any kind of pressure to the observations to create data. So whatever it is that we are interested in measuring already exists, and we are just recording what we are seeing when we observe the observations that are of interest to us. Whereas with the designed experiment, we are effectively, I mean, for lack of a better term, we are creating data because we are applying a constraint. And the typical illustration of this would be something like a medical study, like the one that is described on slide 10, where you have patients that are being allocated to different treatments, right? So we're taking this group of patients and we're giving them this drug. We're taking this group of patients and we're giving them this drug, and we're taking this group of patients and giving them this drug. And then we are observing how they respond based off of the drug that they were given. So that would be a designed experiment where you are effectively sort of eliciting a response from the observation based off of the treatment that is being applied to them. So, okay. So we can classify our statistical studies or our we can classify our statistical tools as being descriptive or inferential. The same, and that basically just boils down to, actually, hold on, I'll come back to that, sorry. So we can classify the tools that we are using as being descriptive or inferential. And we are going to see examples of descriptive tools and inferential tools in this class. So we will look at many different types of descriptive statistics. That's the focus of lecture set number 2. And then we will build up to and look at many different kinds of inferential statistics. And that's essentially the focus of lecture sets 8 through 13. But in between, we're going to do some background and foundational work to get ready for that. Okay, and then we can also classify the study, so the experiment itself, as being an observational study or a designed experiment. And we can classify the study as being a descriptive study or an inferential study based off of the goal of the study. I said study a lot in that sentence. So we can say, for example, this was a descriptive statistical study because the results are simply giving us descriptive statistics about the sample that we are working with. Whereas with the inferential studies, we will typically conclude those by making a broader statement about the population that we are interested in as a whole. But again, we'll see lots of examples of this a bit later on. The point is just that we can differentiate based off of the goal and where the data actually comes from. Okay. All right, so sampling is going to be a very important concept in terms of collecting information so that we can make a statement about different populations moving forward in the course. Now, when we are talking about sampling, we are effectively talking about the process by which we pick observations from the population that we are studying. So if I was going to study, all students at MacEwan, and I wasn't able to collect information from every single student, and there's a variety of reasons why this might be the case. Maybe there's a time constraint on the study. So I need to speak to every single student at MacEwan, but I only have 2 weeks to do so. So it's not, feasible to reach out to and get the information back from every single student in that timeline. So instead, we're going to sample a subset of that population of interest. So we're only going to take a smaller collection of students, and we're going to use them to describe the larger population. All right, now there are actually a number of different ways that you can go about collecting the sample. Very simple ways of doing this would literally just be, having a number assigned to every single person in the population of interest. So say, again, we're going to study all of the students at MacEwan. I actually don't know how many students are at MacEwan, but let's say there's 14,000 students at MacEwan, something in that area. You could do something as simple as saying, give me label every person in alphabetical order. So starting with the first person on the list, they're number 1, all the way down to the last person on that list, number 14,000. Just send me information for the first 20 people, and that's going to be my sample. And that would technically be a sample, right? That's a subset of the population. There's no issue with the definition being incorrect in that sense. The issue is that is probably not going to be the most representative sample. When we hand pick or select observations to enter our sample based off of in that case, convenience, or just based off of the information that's readily available to us, we run the risk that we're not going to get what's called a representative sample. And when we say representative, we mean a sample whose characteristics align with the characteristics of the population. So we tend to think of the populations that we are studying as being dynamic systems with many different features. And you can, in the context of something like the student body at MacEwan, you might be able to appreciate this definition, because if you think about all of the different unique characteristics of an individual person and then extrapolate that idea to a larger collection of people, you can imagine that this system of people is going to have many different features. There's going to be a lot of different ways that we could describe or represent this entire population because of all of the different features of the individual person that's now being, well, again, extrapolated across the entire population. So in order to try and collect a representative sample, so a sample that reflects the characteristics of this larger population, we typically use what we can refer to broadly as probability sampling. So instead of just taking whatever information is readily available to me, I devise a scheme where I randomly select a different person from the population to enter into the sample. So in that sense, I'm sort of removing bias by not just taking what is the easiest thing, or not just selecting the person that would be the easiest to select. Okay, so there's different ways that we can do this. The most common way of using a probability sample would be through what is called simple random sampling. So this is the simplest technique by which we can select an observation from a population of interest. There are two different types of simple random samples. There's a simple random sample without replacement. So this would be a sample where each of the observations in the sample are unique. So there's no repetition. The second is a simple random sample with replacement. And this would be a sample where an observation can appear multiple times. Okay. In simple random sampling, every single population element is given the same chance of being in the sample. So if you think of the population of MacEwan students, which might have a size of 14,000, under a simple random sampling scheme, each person has a 1 over, well, the first person would have a 1 over 14,000 chance of entering into the sample. If you are sampling with replacement, that would be true for every single observation in the study. So in an SRSWR, which is the simple random sample with replacement, every single observation has a 1 over the population size chance of entering into the sample. Whereas with the SRS, each time a person enters into the sample, they cannot be selected again. So the probability that the next person enters in reduces by 1 in the denominator. But we don't need to worry about that too much for now. The point is just to say that each time you select someone to go into the sample, they have the same probability as the next person of being selected. Okay, furthermore, we can say that the probability of observing any sample is the same. And I'll come back to talk about this point a little bit, but we did touch on this last time. All right. So let's look at two very basic illustrations of how simple random sampling would work. So I have been using an example where the population has a size of 14,000. So I've been talking about MacEwan students in the context that there are 14,000 students at the university. Again, this probably isn't the right, this is not the right number, but just for illustrative sake, that's the number that I've gone with. Now let's drastically reduce that. Let's say that our population only has 3 people in it, okay, or 3 observations. So that's what is being indicated here. Okay, so this is going to be observation 1. This is going to be observation 2. And this is going to be observation 3. So we have 3 people in the population. It's a very small population. Now let's suppose that we are going to collect samples, simple random samples of size 2. So from the 3 people, we are selecting 2 persons. How many different samples are possible under this scheme? All right, so sample number 1. So one possibility is if we have 3 people and we select 2 to enter into the sample, what we could get is curly brackets, there we go, is a sample that consists of observation 1 and observation 2. So this is one of the possible samples that we could observe under a simple random sampling scheme if we are taking 2 persons from 3 total persons, or 2 observations from 3 observations. Another possibility is that we observe the sample 1, 3. So this is the situation where we're taking 1 observation, or sorry, we're taking 2 observations from the 3 total persons, but instead of getting the second observation, we're getting the first and the third. And then the last possibility would be the sample with 2, 3. All right. So if we are using simple random sampling and we have 3 total population elements and we only collect 2, there are 3 different samples that we could observe in that situation. Okay, you'll notice here that since it's an SRS, each of the samples have no repetition in them. They're all containing unique elements. So sample 1 contains 1 and 2, sample 2 contains 1 and 3, sample 3 contains 2 and 3. Okay, so that's what I mean by unique. There's no overlap. Whereas if we consider the same situation, but we collect simple random samples with replacement. Okay, so here we could end up with the exact same first 3 samples that we had above, right? So it is still possible that our first sample contains observation 1 and observation 2. And then it's still possible that our second and our third samples contain observations 1 and observation 3, and then observation 2 and observation 3. But since we are sampling with replacement, it is also possible that we observe a sample that is composed of observation 1 both times. Similarly, we could also observe a sample that's composed of observation 2 both times, and a sample that's composed of observation 3 in both spots. Right. Okay, so this is meant to be an illustration of the difference between those 2 sampling techniques. So simple random sampling and simple random sampling without replacement. So these are 2 different ways that we can collect a random sample from some population that's of interest to us. And the difference here is simply that with SRS, each of our samples will have will have unique elements in it. Whereas with SRSWR, the samples can have repetition. So you can observe a sample that has the same number repeated any number of times. Okay. What would the point of SRSWR be? Sometimes the populations you're working with are really small. You still want to be able to make statements about the characteristics of the population. So in that situation, you can sample with replacement to make statements about those characteristics. There are applications. That's good to know. So I was way off. There are applications and there's processes that we study at higher level statistics courses that show the value of sampling with replacement. So there is procedures like a bootstrap, for example. They're not things that we're going to get into a lot. We're not going to talk about that at this level, but there are real applications that use SRSWR in order to build samples so that we can talk about the characteristics of the population. Other questions about sampling, if any? Sorry, part B of the assignment. Yeah, I'll come back to that later though. We can talk about the assignments closer to the end of class. So I'll go through, keep going through the material, and then maybe in the last 5 minutes or so, depending on where I finish up, we can talk about that. Could this skew results in favor if what you want it to look? I think what you're trying to ask is like, all right, so if you sample, like, so say that you hand select observations from the population to be into your sample because you have some information about the characteristics of those observations. You could definitely bias your results toward what you would like the result to be. And that happens in practice, which is why it's really important to ask where the sample came from in every situation that you observe. So even when results are reported anywhere, it doesn't matter what the source is. Whenever you read a statistical result about whatever it might be, it's always important to ask, where did the data come from and how large was the study? Was the study vetted? Like, so were the observations randomly selected or were they handpicked? Because if they weren't, then it most certainly could lead to the outcome that you would like to see. Though we should never conduct a study saying we want to see this particular outcome, but of course that happens. The idea with the simple random sampling, so with the probability sampling, is that we are trying to avoid that. So these illustrations on slide 15 are very naive illustrations because the population only has 3 elements in it. But if you were to imagine the 19,000 students at MacEwan and you were to collect a sample of size 3,000, but you randomly select each of the observations to be in the sample, by doing that, you are following a mechanism that should reduce bias as much as possible. And we can actually show that this is true through theoretical results. But the point is that randomly selecting, so not giving preferential treatment to any observation, is the best way to avoid those biases. Okay. All right, so that's all I'm going to say about sampling. We have a few more definitions to get through before we finish lecture set 1, and then we can start the lecture set 2 material. Okay, so with that being said, the remaining definitions in the lecture set are related to types of variables and types of data. These definitions are actually the same. So what we really need to do is just define what a variable is and define what data is. These are actually, well, not to say that other definitions are not important. These definitions are ones that we will continually see throughout the semester, particularly the definition of the variable of interest. This is something that will come up a lot, but students tend to have a difficult time differentiating between what the variable is, what the data is, and how to describe that. And with that difficulty comes some misconception in how you're supposed to handle different types of questions and what it is that you're actually measuring. So these are the kind of definitions, though, that they'll probably seem fairly straightforward to you in the beginning, but it's something that you'll want to try and internalize as much as possible as you work through the semester, because again, these preliminary definitions really set the foundation for the actual analyses that we are going to conduct later. All right, so first of all, what is a variable? Very simply, the variable is, sorry, one second, Lauren. The variable is the value that, or the unit that we are actually studying in a particular experiment. So it describes the outcome of interest to us. When would simple random, and then sorry, there was a question, I just didn't see it. When would simple random sampling be best, large or small population? That is a good question. So in both situations, you can use it. If the population is small, like really small, then there's going to be a smaller number of unique simple random samples that you can actually use. So in that situation, you might want to consider using an SRSWR just to get a bit more information. But if the population is really small, this is going to create, even with SRSWR, you can run into the same issue because you might over exaggerate a particular feature. So for small populations, there's always going to be difficulty when collecting samples. And actually, if the population is small enough that you can observe all of the elements, that realistically would be the best thing to do. Being able to take all of the information, if it is available to you, is always better than being able to take a subset, because the more you know, the more informed your decision is going to be. So to answer the question specifically, it depends on how small it is. If it's really small and you can just take everything, then you should just take everything. But SRS is a perfectly valid technique for both large and small populations, to such that you can take random samples. The point, okay, so SRSWR and SRS are two different ways of collecting a random sample. In SRS, you have no repetition in the sample, and in SRSWR, you would have repetition in the sample. Both of them have merit, and both of them are used in practice. Most often, in the majority of examples that you're going to see in this class, we use SRS. So we don't take, or we do not repeat any observation in the sample, because we are trying to essentially capture as much feature in the population as we possibly can. And in doing that, we are taking unique observations such that we get kind of like a wider picture, if you will, of what the population might look like. SRSWR is still a valid technique, but it has different statistical properties in the terms of the estimators and whatnot that arise from it. So these are things that we're kind of getting beyond the purpose of this lecture now, but it is a valid technique. And there are situations, like for example, where you have smaller population sizes where you can use it, and it has been shown to give effective estimation properties in those particular situations, even though you might not think conceptually that it would work well for the smaller populations. Just kind of starting to ramble here a bit. I'm going to try and bring it back on the tracks a little bit. Okay, so to the first question, SRS is going to work really well if you have a large population and you collect enough information. For the smaller populations and you're using simple random samples, it's going to be a little bit, well, it really just depends on the scenario and how small the population is. Like, it's hard to say for sure when it's going to be better than the other one. Both SRS and SRS-WR have good statistical properties in the context of the estimator, so they can both be perfectly valid in either situation. The point of SRS-WR is not necessarily not to collect more information than SRS. It's just a different way of collecting a random sample. There are actually, there's a third-year class at McEwen called Sampling Theory, and we teach, I don't know, let's say something in the neighborhood of 6 different sampling approaches that are all probability sampling approaches. So there's lots of different ways to collect information, and it just depends on the context of the problem that you are looking at. So what kind of population are you working with? And what are the characteristics of how that population, essentially. Hopefully that is somewhat answers the questions. Right. Okay, so the variable. The variable is the unit that we are measuring in a particular study. Okay, so there are 2 types of variables, the quantitative variable and the qualitative variable. A quantitative variable can be discrete or continuous. And again, here we're going to get into a little bit of a wishy-washy area where, in talking about the differences between discrete and continuous variables, there will be some overlap depending on the context of the problem. In general, we think of a discrete outcome as being a count. So a quantitative variable is a numeric value, whereas a qualitative variable is typically a written description of a particular outcome. Okay, so for example, a qualitative variable could be a label like hair color or gender. These 2 variables would both be considered qualitative. Hair color is not a quantity, it's a description, you know, like brown, red, blonde. And then gender, same idea. So we would have the different possible gender outcomes, and that would not be a quantitative outcome, it would be a qualitative value because it describes the gender of the person. A quantitative outcome is a number, so this is an actual value. And for the most part, we will be working with quantitative variables in this course, though we will see ways of handling qualitative data as we progress through the semester. Okay, so discrete quantitative variables are numeric values that typically appear as whole numbers. So a discrete variable is typically described as a count. Okay, so for example, the number of TVs in a household. So if you go to a different house, if you go to a house and you count how many TVs are in the house, you might end up with something like 5 TVs. Typically, these are whole numbers, and it would be difficult to, it's not necessarily realistic to imagine that you're going to run into a house where you would have a non-whole number count, though I guess you could have 4.5 TVs if you, I don't know how you would do it, but you could. I guess, cut a TV in half and throw the other half out or something. But for the most part, we're talking about whole numbers that represent a count of the number of items, for example, in a household, number of TVs, number of cars, number of computers. This would typically be a discrete quantitative variable. A continuous variable is something that can be measured, or essentially what it is a value that can be measured to a very precise number of decimal places, if you will. So things like weight and height, theoretically, you can measure these very precisely. So past just the whole unit. Usually when you measure your weight, actually, this isn't true. So like, for example, if you stand on a scale and you measure your weight, usually you're going to get a decimal place of accuracy associated with that value. So very rarely, well, most often I think that when you measure weight, you don't just take whole numbers, you usually take it to some decimal places of accuracy. And you can measure those decimal places beyond just the first unit. So you could be not just 182.7, but you could be like 182.73625. So this would be a quantity we consider to be continuous. Same thing with height, same thing with a time measurement. Though again, this is where you can start to get into a bit of a discrepant, or you can start to imagine there's a bit of overlap when you're talking about time. You can measure this maybe just as minutes, but you could easily measure it, to the nanosecond if you had a machine capable of that. So the continuous variable is one that can be measured to some number of decimal places of accuracy, or as we like to say, more precisely than just a count, which is a whole number value representing, the number of items in a house, for example. All right. So data represents or is defined as a collection of units on a particular variable. So let's say our variable of interest is age of students in this class. Okay, so our variable of interest is the age of the students in this class. Let's say that I take 10 students and I collect their individual ages. My data is now those 10 measurements. So the variable is age, the data is the actual set of values of ages that I have collected from the population of interest. Data can be described in the same way as the variable. So you can have qualitative data, you can have quantitative discrete data, you can have quantitative continuous data. And the definition of that would follow exactly from what it did for the variable. Okay. So qualitative data would basically just be categorizations or labels like hair color. Discrete quantitative data would be data that represents a count of some object that belongs to each person in the sample. And then continuous quantitative data would be some measurement of interest for each of the persons in the sample. Okay, so to illustrate this, I'm going to use a very simple data set that contains the top 6 point scorers from the 2020-2021 NHL season, so last year's season. So in this data set, we have 6 observations. Okay, so these are the 6 observations. Okay. All right, and then we technically have 1, 2, 3, 4, 5 variables. Okay, so the player name, the team name, the number of points scored, the points per game played, and the power play goals scored. These are the variables that are of interest to us. Yeah, age is always one of the ones that comes up. Sorry, this is a question in the chat. Age is always one of the variables that comes up as fitting in between them, like in between the category of continuous and discrete. Typically, the way that I tell students to handle this type of variable right at this level is just to kind of think of it, is to look at it as it appears. So if the age appears as a whole number value, so say you're just measuring age as years and you're not considering anything else, you're just going number of years you've been alive, that would appear as a discrete quantitative variable, right? Like this person is 22, this person is 26, that person is 34, that person is 7. But you can imagine that age, when you think about it, like if you think about age in seconds, like that is certainly now continuous because it's continually updating. Every second we're getting 1 second older, right? So it just depends on how it's being portrayed and the situation in which you want to evaluate it. The other thing is with age, if someone was to say to you in a study, we found that the average age of students in first year statistics was, I don't know, 19.7 years old. That the 0.7 that's attached there would make sense. Like you wouldn't think of that and go, okay, well, it has to be a whole number. You would basically think, okay, that just means, they're a bit closer to 20 on average, but there's enough people that are 19 that it kind of drags the value down a little bit. So in that sense, age is often treated as continuous and expressed in a continuous way, and that has meaning to us. So again, it's a value that kind of floats the line a little bit. In certain contexts, it is just a count, but if measured precisely, like to the minute or to the second, it's very clearly continuous. So it depends on the context and how it's presenting in the particular study. But I think it's one that can go either way in most situations. Again, it depends on when you count it, I guess. Yeah, I guess it could be. Because you could measure it, you could just change the unit that you're observing it with, like instead of doing, even if you didn't do years, it is fixed now at a particular value. So I could see an argument for that. Yeah. Any other questions? Right. So the example, just to illustrate the definitions of the variable, the data, and those 3 different types. All right. So we have 5 variables, which are the player, the team, points per game, and the points per game played. We have 6 observations. Okay. So based off of the definition of data, each collection of 6 observations under the variable is the data, right? So we have, for example, okay, so like these, okay, so this would be data for power play goals. Okay, so the data is just the collection of observations attached to the variable of interest. And this would be the same definition for each of the different variables. So for points per game played, you have the 6 observations for points per game played. For total points, 6 values. For the team, 6 values. And then for the player, 6 values again. All right, so there's a few questions here that correspond to this particular data set. So what type of variable is player? Okay, well, player is going to be a qualitative variable because a name of a person is essentially a label that defines the person, and it's clearly not quantitative. So the qualitative variable would be the logical choice to describe this. What type of variable is points? Okay, so in the simplest situation, we would consider points to be a count of the number of goals and assists that you have accumulated across the season. So this would be a discrete quantitative variable. All right, part C, what type of data are provided in the points per game played column? Okay, so points per game played is now effectively an average of how many times you score per game. You can see here that this data is measured to 2 decimal places of accuracy. So this would be an illustration of data that would be quantitative because it's a numerical value, but it's continuous because we have some number of decimal places of accuracy by which we can measure this value. And you can imagine that if I wanted to, I could do this to 1 decimal place or 4 decimal places. It's easy to extend. In this case, I'm only using 2, but the point is still that this is no longer a count. This is now effectively an average or a ratio of how many times you're scoring per game. So this would be an example of continuous quantitative data. And again, the definitions here, so qualitative, discrete, quantitative, continuous quantitative, they are the same regardless of whether or not you're talking about the data or the variable. Okay? The variable is simply what you are measuring. The data is the collection of values for that variable. But if the variable is discrete quantitative, the data will be discrete quantitative as well. And then finally, what type of data are provided in the team column? This would be the qualitative data. Okay. Any questions? All right. Okay, so that brings us to the end of lecture set 1. So again, lecture set 1 is effectively a lecture set that deals with definitions that are going to be utilized throughout the course. The key definitions are the definition of statistics, the types of statistics, so inferential versus discrete, population versus sample. This is a concept that we're going to come back to quite often throughout the class, particularly in the second half when we talk about statistical inference. In addition to that, we've talked about observational versus designed experiments, the type of study. We talked about sampling techniques, and then we discussed definitions of variables and data. Now, the definitions of variables and data lead us naturally into the next lecture set, which is about organizing information. And what we will see is that the way that we organize particular data is based off of the type of data that we are working with. At the end of the first lecture set, there's an exercise for you to use that kind of encompasses everything that we talked about within this lecture. When I post the completed lecture set notes, I will also post the solution to this exercise. So go ahead and try this, and then you can compare your solutions to the solutions that I put up for the problem. And if you have any questions, you can let me know about that once we get to it, or during like an office hour at the start of, before the start of class or something like this. Okay, so we still have some time left. So I'm gonna get into the second lecture set. So as I said before, the second lecture set is essentially focused on describing data. So the second lecture set is going to be comprised of graph construction and numerical measurement. So we're actually going to start to see examples of how we can describe a particular set of data using numerical value and visual tools. As I had just mentioned before, the type of tool that we utilize depends on the kind of data that we are working with. So those definitions, qualitative, continuous quantitative, and discrete quantitative, are important definitions because they will inform our choice of graphical procedure and numerical measurement. This particular lecture set is comprised of descriptive tools. So whenever we use values like the mean or the median or standard deviation, as we will see later on, so individual numbers that summarize what we have observed, we can think of that as a descriptive measurement. Okay, so everything that we're going to study in the second lecture set would fall under the umbrella of a descriptive statistic. And that includes the visualizations, so the graphs that we're going to look at. So those are descriptive tools that would be a part of the descriptive statistical tool bench, I guess you could say, or like toolbox, if you will. Okay, so we're going to start by discussing how we can summarize qualitative data. So on slide 4 of lecture set number 2, we have a qualitative data set. In this data set, we have the era, or we are observing the era in which a classical painter went to school. So the era here, this is the variable of interest. Okay, so this is the thing that we are actually measuring or writing down. Okay. Okay, and then it should be clear that this is a qualitative variable because what we are writing down is a description or a label that represents when a particular painter went to school. Okay, so our data set is comprised of 50 observations. Okay, so the data has 50 different values, and that's shown in this table on slide 4. In the table, you can see that we have 7 different eras. So there's the Renaissance era, the Mannerist era, the Cinquecento era, the Venetian era, the Lombard, the 16th century, and the French era. So 7 different eras classifying when a different painter went to school. So again, this is qualitative data with 50 observations, and then a qualitative variable, which is the era in which the painter went to school. So that's the thing we are measuring, and we have 50 values corresponding to that variable. Okay, so we're going to talk about ways of organizing and describing a qualitative data set. So the following techniques are going to be appropriate when working with qualitative data. The first set of techniques that we're going to look at are the construction of what are called a frequency distribution and a relative frequency distribution. both of which are quite easy to build. All right, so the frequency distribution is simply a list that gives a count of the number of unique observations in the data set. Okay, so I'm going to show you an example of this in a second. The relative frequency distribution is the same as a frequency distribution, but instead of giving a count, it gives the frequency or the probability of occurrence of each of the outcomes. So a frequency distribution is quite easy to construct. You just list the number of unique items in the data set, and then you give the count of the number of times that item appears. The relative frequency, you take the count for each item and divide by the total number of items. So this table on slide 6 shows the frequency distribution and the relative frequency distribution for the data set of interest. Now, you will see here that I have also included a tally. You don't have to do this. The tally column is simply there for counting purposes. You will also notice that I have the frequency column and the relative frequency column in the same table, but you don't have to do this either. You can have simply, for example, era and frequency as one table, and then you can have separately era and relative frequency in a different table. I've combined them here just for space. It's not necessary to follow exactly the same structure that I have written. So based off of the definitions of the two types of distributions, the first and the third column would be the frequency distribution. Okay, so this column here. So this column here and this column here, this would be the frequency distribution. Okay. So you can see that the way the frequency distribution is constructed is you list each of the unique eras in our data set. So we have 7 unique eras. Again, those are the Renaissance, the Mannerist, the Cinquecento, the Venetian, the Lombard, the 16th century, and the French. The frequency distribution gives a count of the number of times we have observed each era in that particular data set. So if we go back and look at the data, this frequency distribution is telling us that Renaissance appears 10 times. And this is found simply by counting the number of times you see Renaissance in that particular data set. So you can see in the first 2 rows, you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have 10 occurrences of Renaissance. That's where that value comes from. That is a frequency. So a frequency is the same thing as a count. Right. And then in the third and the fourth column, you can see the relative frequency distribution. So if I was to do a similar thing here, right. Okay, so these 2 columns here, this is my relative frequency distribution. And again, you can put these all in one chart, like I have it written here. The tally, you don't have to give it. If you want to, it's fine. The relative frequency, you require the frequency. So you have to have the frequencies in order to compute the relative frequencies. But otherwise, it's simply just a computation that takes the frequency and divides by the total size of the data set. Yeah, column 1 and 4 is the relative frequency. Yeah. And again, this type of chart, this table or distribution, this is what we use to summarize qualitative data. So our frequency and relative frequency distributions are utilized when we want to summarize qualitative information. Okay, now what we're going to do is talk about two types of graphs or charts. These charts, the pie chart and the bar chart specifically, these are the graphs or the visual tools that we utilize for qualitative data. So when we have a qualitative data set, typically our process of analyzing that data would be compute the frequency and relative frequency distribution, and then construct a visualization of those distributions. And that's what the pie chart and the bar chart are. A pie chart is simply a circle where you slice the circle into a number of slices equal to the number of outcomes in the data set. So in this particular illustration, we would have a pie or a circle that's being sliced into seven slices, one for each of the different outcomes. And then each slice is a size equal to the relative frequency. So you can think of a pie chart as a visual representation of the relative frequency distribution. Okay. A bar chart serves the same purpose as a pie chart, except that instead of slicing a circle into a number of pies, you're using vertical bars to represent either the frequencies or the relative frequencies. So a bar chart can be used to display the frequency distribution or the relative frequency distribution. Can't spell. Okay, so constructing both of these objects is pretty straightforward. In the case of the pie chart, we would essentially start with a circular object or a spherical or a circular kind of an elliptical style object that looks like a pie. We would slice the pie into a number of slices equal to the outcomes. And then the size of each slice is going to be essentially, they're going to be relative to each other, but they're going to represent the relative frequencies. So the smallest slice would have the smallest relative frequency. The largest slice would have the largest relative frequency. And then slices will be given the same size if they have the same relative frequency. A bar chart is slightly different in that it uses axes. So to construct a bar chart, we would start by sketching out an axis, an X and a Y axis. On the X axis, we would write down the labels. On the Y axis, we would write either the frequencies or the relative frequencies, and then we would draw a bar to the height of those values. So something like this here would represent these would be representations of the bar chart and the pie chart for the data set on era of classical painter. So you can see for the pie chart, we started with a circular object. We then sliced the circle into 7 different slices, right? So we have one slice for each of the different eras in which a painter went to school. Okay, now the pie chart is showing you the percentages, but this again is the relative frequency just multiplied by 100, right? So this is going to be 0.2. This is going to be 0.12. This is going to be 0.1. This is 0.14. This is 0.2, 0.12, 0.12. Okay, so we have our 7 slices shown here. You can see that the Renaissance, which has the largest relative frequency, has the largest slice in the circle. You can see that the French, the Mannerist, the Seicento, they all have the same relative frequency. So those 3 slices, the pink, the yellow, and the sort of highlight green, those are the same size. You can see the 16th century has the smallest relative frequency, so that's the smallest size. Venetian, so the Venetian and the Renaissance have the same relative frequency, so those 2 slices are the same size. And then the Lombard is a unique size of 0.14. So its slice represents that size relative to the other slices in the pie. For the bar chart, you can see that on the x-axis, we have the labels. Okay, so each of the different eras are shown on the x-axis. So we have a label here telling us what the axis represents. Then we have each of the different possible outcomes. So Renaissance, Mannerist, Seicento, Venetian, Lombard, 16th century, and French. And then on the y-axis, we have another label telling us what the y-axis represents. So in this case, relative frequencies. Again, you don't have to use relative frequencies for a bar chart. You could also use frequencies. So if we wanted to, we could change the label here to say frequency, and then we would just change what's written on the y-axis to represent the counts. So instead of having 0, 0.05, 0.1, 0.15, and 0.2, you might go like 0, 2, 4, 6, 8, 10, 12, for example. And then you would draw the bar to that frequency. The interesting thing is the frequency bar chart and the relative frequency bar chart are actually going to look exactly the same. It's just the label of the axis that is going to change, right? And then you can see that the height of each bar is being drawn to the relative frequency. So here, for example, we have 0.2, which is the same thing as 20%. So you can see that the bar is just getting drawn to the relative frequency of interest. Okay. All right, so I'll just quickly say that the pie chart and the bar chart, these are our tools for representing qualitative data. So far in lecture set 2, we have talked about the frequency and the relative frequency distribution, which are unique to the qualitative data set. And we've talked about the pie and the bar chart, which are unique to the, also unique to qualitative data. Okay, so next class, what we will do is we will start by talking about how to organize quantitative data. And you'll see that this is a similar process in the beginning in that we construct frequency and relative frequency distributions. But before we do that, we have to construct what are called bins. All right, so I will stop here for today. I had a question earlier about one of the assignment problems, so I'll come back and talk about that. But if there are any other questions, I will be hanging around after class for a little bit. And I have office hours at 1 o'clock. Okay, so otherwise, lecture 3 will be recorded on Thursday morning at 8. And again, all lecture material will be posted to the YouTube channel for you to review whenever you can. Okay, so have a good couple of days, and I will speak to you guys on Thursday morning.